So this will be joint work with Cheng Shi, who is here, and Panayotis Kevrekidis and Ross Parker. I particularly want to emphasize the contributions of Cheng Shi, who's a fourth-year graduate student in applied math at Columbia. So just before I start with the slides, I just want to remind you of a very familiar stuff. One-dimensional Schrödinger operator with a potential well that decays at infinity, continuous spectrum of radiation modes from 0 to infinity, and a single bound state. So that's the first cartoon. The second is a double well. If the wells are separated, you have nearly degenerate eigenvalue. And now if I have nonlinear, oh, I forgot the nonlinear term. What do you do? Yeah. That's better. So nonlinear term. So this is an attractive nonlinear term. Then what happens is for small amplitudes, the ground state energy bifurcates into a branch of nonlinear bound states, which keep the symmetry of the potential. But then at sufficiently large amplitude, it's energetically preferable to put more L2 norm into one of the well or the other. So this is now a symmetry breaking. So you have states that look like this, and these become the stable states of the system. And this is there are really two curves here, because one could be concentrated on the left well and the other on the right well. Okay. So let's just keep that in mind. Okay. Okay. So waves in media with flat band spectra. So there is significant interest in the dynamics of waves in crystalline media which exhibit flat or nearly flat band band spectrum. And here's an example. So I'll show you lattices in a little bit, but here is the band spectra for the Kagome lattice. The Kagome lattice has 3 atoms per unit cell, and the underlying Bravais lattice is the equilateral triangular lattice. And there you see a flat band at the top, tangent to a dispersive band. These two bands touch. They touch in Dirac points, but really my focus will be really what happens at the top, okay, top of the spectrum. So these are the 3 dispersion surfaces of a nearest neighbor Laplacian on the graph, okay? And I'll write down what these things are. Flat band spectra give rise to localized, non-dispersing wave packets. If I make continuum superpositions of the plane wave-like states associated with the flat band, then I'll get wave packets or what are often called quasi-particles. And these are of interest in various fields. In fact, systems with flat bands are of interest because of strong interactions, electron-electron or light-matter interactions that you could get in condensed matter, or in things like photonics or metamaterials, nonlinear effects. And the kind of platforms where people see them are, for example, twisted bilayer graphene or resonator arrays with various geometries. And because of this interest, we're interested in studying the types of stable and long-lived localized excitations that arise in nonlinear wave models on such multi-lattices, which have support a flat band. And this particular investigation was originally motivated by an article in PhysRev A by these authors in 2013. Okay, so now we step back. So this is the nonlinear wave model. This is the nonlinear wave model, the nonlinear Schrödinger equation. This will be a Laplacian on some multi-lattice, L. I'll be precise a bit later on. And psi is a complex-valued, time-varying potential wave function on this lattice. And of course, this is a self-adjoint operator, and the nonlinearity is real. So the L2 norm is preserved. This is either the optical power in the optics setting or for something like the chemical potential if you were looking at this as a mean field limit in many-body physics. And we're interested in nonlinear bound states. Yeah, the nonlinearity in this discussion will be taken to be defocusing. It'll be a repulsive nonlinear term. So plus, or more generally, psi to the 2 sigma, because we'll want to understand how the wave properties vary as you move some parameter in the nonlinearity. So nonlinear bound states are standing wave solutions, and they satisfy an equation like that. This is, again, a discrete operator on the lattice, and this is a on-site nonlinearity. And just as a summary of where we're headed, it turns out that, for example, suppose you took the Kagome lattice. That's the gray lattice in the background in these 3 figures. So there's a linear flat band spectrum, as we saw, and that the linear flat band spectrum has associated with it compactly supported flat band eigenstates. Okay, so that's a remarkable thing. You don't see that for continuum PDEs, but in discrete operators, you can for certain lattices. There are compactly supported states, and that these actually, because of the on-site nonlinearity, give rise to compactly supported solitons, okay, genuine nonlinear states of the system. And here are 3 of them. This is a 6-site state. This is a 10-site state, 12-site state. You can make many of them. You could separate them. So the hexagonal state, this particular one is the one of interest to us here. The hexagonal state is a minimal compact soliton. Okay, so this is going to be a soliton of, say, smallest support with all of the symmetries of the Kagome. So we're going to be studying these kinds of states. And the main result is going to be a sharp criteria for the dynamic stability of such states on general multi-lattices with flat bands. Okay, so we start with the lattice, a Bravais lattice. That's just an integer linear, that's just a span of D linearly independent vectors in Rd. There's a dual lattice. They satisfy the usual relations, and the Brouin zone is the Voronoi cell associated with the dual lattice. It's all points in R2 in momentum, which are closer to the origin than to any other latticite. And a multi-lattice is just going to be the union of n, capital N, interpenetrating copies of the Bravais lattice. So L could be viewed as a union of n of cells, and each cell has n atoms, capital N atoms. And a wave function is just a function on this discrete set. And a Laplace type operator is denoted by Laplacian sublattice, where we sum over nearest neighbors with some coefficients, some weights, where the weights are real and symmetric. Okay? And as a consequence, this is a bounded operator on little L2, square summable wave functions on the multi-lattice. So I want to assume some translation invariance. So we're going to take W of x, y to be periodic in x and y. So for each k in the Brouin zone, right, I want to get the band structure. The band structure is I fix k in the Brouin zone, and for each fixed k, I study this eigenvalue problem, the pseudo-periodic eigenvalue with quasi-momentum k. And this is a self-adjoint eigenvalue problem. So there'll be n eigenvalues, the number of atoms in a cell. Those eigenvalues are continuous, Lipschitz continuous functions of k, and these are the associated eigenvectors. And if you take them all together, they're complete. I can construct any state in L2 of the lattice by taking appropriate superposition. And this collection is called, this totality of maps together with the eigenmodes is called the band structure. Okay. And in particular, the spectrum of the minus the Laplace operator will be the union of the images of the Brouin zone under these continuous map. So it's the union of intervals, which could overlap, of course, and they touch at these degeneracies. Okay, so that's just to set notation and terminology. So here are some lattices: diamond lattice, Kagome lattice, checkerboard lattice. Okay, and each of them, you'll see. Okay, so here I indicate for the diamond lattice the right. It's a nearest neighbor operator, but the hopping coefficient is not uniform. The vertical hopping coefficient is 2, and the others are 1. And for this choice of hoppings of the nearest neighbor operator, you get a flat band, which is tangent to the upper band, the optical band. Right? And similarly for the Kagome, here all the hopping coefficients are uniform. They're all 1. And here's for the checkerboard. So within the dashes is just a unit cell. So this is 3 atoms per unit cell. And then you translate. And the Kagome also has 3 atoms per unit cell. And you translate by the vectors of the triangular lattice. And in the checkerboard, we have 2 atoms per unit cell. And we just translate by the vectors of the square lattice. Okay? Here there are 2 bands, 3, 3. Okay? And in each case, the flat band sits at the top. Okay? If I change this coefficient from 2 to something else, I can move the flat band up and down.
All coefficients in checkerboard the same?
Yeah. Okay. So there are some general mathematical results on this, and going back to work of Peter Couchement, and then Cheng Shi proved the following: that suppose you have a flat band. Okay. So I omitted something from here. First of all, if you have a flat band, Couchement proved that it has a compactly supported eigenstate. Okay. And what Cheng Shi showed is that the set of all translates by the underlying Bravais lattice of that compact supported state is dense in the little L2 space. So I'll give examples of compactly supported eigenstates in a moment. Okay. So there are various general results that one could show about flat band systems. So I want to focus on minimal compact flat band states. So this is still the linear problem. A minimal compact flat band state satisfies a number of conditions. So first of all, it's an eigenfunction with the flat band energy and then there's some symmetry which is cyclic and of even order. With the property that if you take this eigenfunction, well, this support of this eigenfunction is going to be compact, and so it'll be some say finite set of points, and you can move from one point in the support to the next by acting with the symmetry of even order. Okay, and so the support here is equal to S, which is the order of the symmetry, and that equality of number of elements in the support and the size of the group of symmetries is why we call it minimal, because you could get much larger. The symmetries of the lattice might not take you all over the support of might not visit all the sites of the support of a larger hexagon or whatever state you have. So this induced symmetry also commutes with the Laplacian. Okay? And the state is going to have a certain homogeneity. Its amplitude is constant on the support, and it's sign alternating. So it's something that looks like that. I could represent the states in this form. And in all of the examples that I wrote down, there are such states. It's basically -1 + 1 -1 + 1 on a very, very symmetric set that you could move along with the symmetry of the operator of the Laplacian. Okay? That's what a minimal compact flat band state is. Okay, here are some pictures. So this is the same picture as before, only it has some colors on it. Here we take +1 here and -1 there, and that is a minimal compact flat band state for the diamond lattice. For the Kagome lattice, it's a hexagon. It's +1, -1, +1, -1 all around. And then for the checkerboard lattice, it's on a square. Okay. So 2 sites, a dipole, 6 site, and 4 site. And okay, now a simple consequence of the nonlinearity being on site is that any of these flat band states extends to a solution of the nonlinear problem. So in the context of the nonlinear problem, I'll call them solitons, which is a very loose use of the expression soliton. It's the same state for any A, right? For any amplitude A, I have a state, and its frequency is going to be now. This is the only difference now. The functional form of the soliton, it's still supported at n sites with the symmetry playing its role, but the frequency now is nonlinear. So f of a squared, f of a squared. Okay. And that gives rise to a time harmonic solution, of course. So these are the objects whose stability I'm interested in. So here's the setup for the statement of the theorem that I'm going to state. Suppose we have a lattice L for which the Laplacian has a flat band, and the flat band occurs at the maximum of the spectrum on top, just as in those examples. And suppose I have a family of minimal compact solitons. These are the solitons that are sort of on some minimal, highly symmetric set of L2 norm of power equal to nu. So recall that the states look like this. Okay, so if I want the ones that have little L2 norm squared or power equal to nu, then I just have to adjust the A to depend on nu. And here the nonlinear frequency is given here because I'm taking the special case of this homogeneous power nonlinearity. Now, I want to say what it means to be stable, and so one has to be careful there. So we're in a Hamiltonian system. This is an infinite dimensional Hamiltonian system. Here's the Hamiltonian. This is the potential term, the kinetic term. The L2 norm is a constant because the equation is invariant under multiplication, the multiplication of the wave function by e to the I theta. So you have these two invariants. And nonlinear bound states are critical points of this functional. If I write down this functional over here, then if I just do the first variation, I get the equation for nonlinear bound states. So that's the first thing I want to observe before we say what stability is. And because the equation has this invariance under multiplication by e to the I theta, the right notion of stability is the stability of the orbit, of the group orbit, okay? It's like, if you think of solitons and water waves, right? If I take a small perturbation of a soliton water wave, if I change the amplitude, it might start going faster, and so you have to change, you have to somehow dial up the shape, make the soliton travel in some way to match the perturbed solution. So this is a standard notion of stability in Hamiltonian systems. It's going to be stability modulo some group. Okay, and I want to talk about nonlinear stability, which is not trivial in Hamiltonian systems. And if you're working in dissipative systems, linear stability, just looking at the linearized spectrum, very often implies, by kind of standard arguments, nonlinear stability. But in Hamiltonian systems, nonlinear stability is a bit trickier because you could have linearly stable systems, but due to resonance, you can lose stability. Okay, so we'll talk about nonlinear orbital stability, and that's the statement that if the distance of the initial condition to the orbit is small, then the distance of the solution to the orbit is small for all t. Okay, and what do I mean by distance? It's just a solution of a least squares problem. It's just the minimal distance of psi to anything in the orbit. Okay. So here is the theorem. Suppose I have a minimal compact soliton of the defocusing discrete nonlinear Schrödinger equation, which is living on a lattice with a flat band. There exists a critical value of the nonlinearity parameter. So there's a critical value of this sigma here, such that if you are below that, if you're not too nonlinear, right, then there's some threshold below which the solitons are stable, or are nonlinearly stable in the sense that I stated. And if you're larger than that threshold, then you're unstable. If you're above this threshold, then all of the minimal compact solitons are unstable. Okay, and just to elaborate a little bit, when I say orbitally stable, what's underlying it is that this psi. Remember that psi nu, these solitons are critical points of some energy functional. Well, the claim is that they are actually local energy maximizers of the Hamiltonian subject to fix n. That's really what's making them stable, nonlinearly stable. And in the cases where psi nu is not stable, then you could actually display exponentially growing modes, and there the linear stability will imply nonlinear stability. So let me stop there for a moment. There's a lot on that slide. So are there any questions?
So what's the critical What's the value of the critical sigma?
Well, we have a way we have an analytic characterization of it. Okay, and it's going to be different for different lattices.
Typical values?
Typical values. 1.4. And then in some lattices, it might be 0.8.
So less than 2?
Can be less. 2 is not cubic, it's fourth power, right? So you're thinking of 1, right?
Oh, sorry, yes.
Yeah, right, okay. It'll be clear from the analysis how you decide where that threshold occurs. Okay, so this is an illustration of the stability-instability theorem. Okay, so this is some measure of the amplitude. This is the little L2 norm. This is the band spectrum, and this is the top of the spectrum. This is the flat band energy. Okay, and so what you now in blue are the minimal compact soliton states, which you see if you're in the subcritical regime, they go unstable at some L2 norm, and then when they go unstable, there's a symmetry breaking bifurcation. Okay, what happens is instead of getting, say in the Kagome case, instead of getting this sort of local energy maximizer, which is hexagonal and of equal amplitude on the sites, what happens is that it becomes asymmetric. There's a symmetry breaking. And there could be multiple symmetry breakings along this curve. But if you're above in nonlinearity, what happens is the minimal compact solitons are always stable. Always unstable, sorry, always unstable, and you still get these bifurcations. Okay. So in order to, so for the rest of this talk, what I want to do is say something about the actual proof of that result on stability and instability, and the approach that we take. We have a variational perspective on this, and it actually is influenced very much by work in the 1980s on stability of solitary waves of equations like the nonlinear Schrödinger equation or nonlinear Klein-Gordon equations and water wave models like KdV and things like that. So the framework has some analogies, but the actual implementation of it is quite different. Okay, so as we saw, minimal compact solitons are critical points of this energy functional, H subject to fix n. So psi satisfies, first variation is 0, and what I want to do is I want to use this energy functional as a Lyapunov functional. That's going to be what's going to capture my, my solution trajectory. Now, let's suppose we start evolving with some initial condition. Now, at every time, so now suppose my initial condition at time 0 is near the minimal compact soliton. So psi of 0 is near the orbit. Then for every time, once I turn the time on, what I could do is solve this least square problem. I just minimize. I pick a phase such that this distance from the orbit is minimized. So this is theta star is the value of the phase shift for which the distance to the ground to the minimal compact soliton orbit is minimized. Okay, that's a definition of theta star. So now what I could do is I could express the deviation. I could express the deviation from the orbit as u plus iv, where u and v are the real and imaginary parts of the perturbation. And then I just apply energy conservation. So the energy of the initial condition minus the energy of the compact soliton, minimal compact soliton, is equal to this, right? And the reason for that is, well, there's scale invariance of the energy with respect to phase, and also conservation of energy. The energy here is equal to the energy of that. So there I've just used conservation of energy. And then I do a Taylor expansion. So they're going to be first order terms in the perturbation and second order terms. The first order terms drop because psi nu is a critical point. And so what I get here is the second variation. The second variation of E at the minimal compact soliton. It's a quadratic form, and it acts on U and V, and L plus and L minus are operators. They're, in this problem, they're difference operators. They start minus Laplacian on the lattice plus corrections. So here are what the operators look like. So here is the, right, so this is some number, this is a constant, and this is small, because I'm choosing that psi 0 is close to psi nu, and the energy is a continuous function of the field. So this difference goes like that. So, and this is small if I choose psi 0 close to this. And so if this were, say, a positive definite quadratic form, then I'd be done, because it would say that the perturbation remains small for all time. Okay. So let's look at these operators L plus and L minus. What they look like is there's a bulk operator part to it, just the Laplacian shifted by a constant, plus a correction. And the correction is a potential, a repulsive potential, which is supported on the support of the state about which you linearize, supported on the hexagon, say, in the case of the Kagome lattice. Now, in order to so clearly, whether or not this quadratic form is positive definite or negative, or negative definite is going to make a difference. And what we'll see is that to identify when the orbital stability holds, it suffices to explore this quadratic form and show that we want to see when it is negative definite. In that case, if it's negative definite, then it's a local maximizer. Then the state is a local maximum. So that's what the analysis is going to boil down to. And if it's negative definite, that means that the quadratic form has such a bound, and then by continuity, this is small, say equal to something minus epsilon. So therefore, you'd have a bound for all time, and that would be the proof of nonlinear stability. But it's not so simple. So there's bad news and there's good news. So the bad news is that the quadratic form is indefinite. Quadratic form is not negative definite, it's indefinite. It has positive directions. It has 0 directions and positive directions. But the good news is that the functions that you stick into the quadratic form are not arbitrary, right? They come from a solution of they come from the dynamics. And they are constrained. How are they constrained? Well, remember that U and V are chosen to be the perturbation about the optimal choice of point in the orbit. So there's an optimality condition, and that translates into V being orthogonal to the state itself. So if you look at the function that you're minimizing and you compute its gradient, and this is what you get for the choice theta star of t. And then second, well, if I start near, if psi of 0 is near the ground state, that means that the energy, right, the L2 norm is going to be close by continuity of these functionals, and so that means that psi nu is nearly orthogonal to 0. So there really are two constraints on the trial functions that go into that quadratic form. So there's a chance, maybe, so the question is whether these two constraints put you into the negative cone of that quadratic form. Okay, so let's look in detail. So here's the quadratic form. These are the constraints. And the first observation is that just by writing, first let's look at the bulk part of the operator. The operator has, right, a bulk part and this is the bulk part, and then there's the part that you add to it, which is supported on S sites. The bulk part of the operator is strictly negative for positive amplitude states. So that's the continuous spectrum. That means that all of the discrete spectrum has to live between a negative number and infinity. Okay, now regarding L minus, so now I add in the compactly supported term in the operator, the part that's supported on the S sites. One could check that L minus acting on the soliton itself is equal to 0. So that says that already that it can't be negative definite, so it's actually less than it's a non-positive operator, but it's not a negative operator. But V is constrained to be orthogonal to psi, and so therefore it is negative definite. So this is a explicit calculation and not difficult. Now L plus is trickier. So L plus, if you apply L plus to the soliton, you see a positive eigenvalue. So you see explicitly that the quadratic form now has positive and negative directions. And there's one constraint. So the question is whether, if you're orthogonal to this vector, you have a cone, and you're orthogonal to a certain vector, the question is whether this puts you into the negative cone of this operator. And we'll see that that answer depends actually on the amplitude of the states, where you are on the bifurcation on the curves. So the answer of whether you are, this geometric property of this vector falling into the negative cone of this operator depends on amplitude, or L2 norm. Okay, so we have to track the eigenvalues of L plus, and we know that they're in this interval. And there's a useful observation. That observation is that L plus is this bulk operator, right? This is the band spectrum just translated by a constant, plus a finite dimensional rank, finite rank perturbation. This is a rank S perturbation. It's just a delta function on S sites. Right, so because the support is on these points, so it's either rank 2 in the diamond lattice case, 6 in the Kagome lattice case, and 4 in the checkerboard lattice case. Now, what I have to do is find discrete eigenvalues, and I know where to look because the operators are self-adjoint, so I have to look on the axis, on the real axis. And the natural thing then is to look at the resolvent on the real axis when you're away from the bulk spectrum. But my operator has this form of a bulk operator plus finite rank. So there's a linear algebra trick for an identity called the Sherman-Morrison-Woodbury formula, which is used in numerical analysis and various other areas, which tells you how to write down, if I know how to invert this operator minus lambda, then I can invert the perturbation, okay? So I could express the resolvent of L plus, the thing I'm interested in, as a finite rank perturbation of the resolvent of the bulk part. If I go ahead and do that, then what happens is that, so there's some expression, and it turns out that you can then reduce the tracking of the eigenvalues of this rank S perturbation to finding the zeros of a determinant, finding the zeros lambda of a determinant of an S by S matrix, which depends analytically on the parameter lambda. So it's not a standard eigenvalue problem, it depends because of the nonlinear dependence on the eigenvalue parameter. And then you want to track those eigenvalues as nu. The L2 norm of the state varies. That's not easy in general. So we want to do something else. And what we do is we use symmetry. There's a symmetry reduction, and this is where the minimality comes in. So recall that psi is minimal, which means that there is some symmetry which maps the support to itself, and to move around the support, you just take an excursion by applying the symmetry S to any point in the support. And so this symmetry on the support, on that S point, set of S points, extends to a symmetry of the operator. You have this commutation. Okay, so and this symmetry, because of its cyclic character, its eigenvalues are the S roots of unity. Okay, so that means we could the natural thing to do then is to decompose the Hilbert space into an orthogonal sum associated with each of these eigenfunctions of the symmetry, that symmetry subgroup. Okay. So here, this is the definition. So L2 omega n is going to be the set of all f in little l2 with the property that if you apply the symmetry, you would just go omega to the n to the vector, to the vector, and there are S such subspaces which give an orthogonal decomposition of the Hilbert space. Okay, because of this orthogonal property of the sum, we see that the spectrum of this operator is now reduced to the union of the spectra of these of the operator restricted to each of these subspaces. So if you're studying the S eigenvalues of some operator, the eigenvalues might collide. They can do all kinds of things, and doing degenerate perturbation theory is kind of tricky. So what this does is it reduces degenerate perturbation theory to perturbations of looking at the tracks of simple eigenvalues. You have a simple eigenvalue moving in each of these subspaces. You totally decouple the problem. Okay, so now that's the bulk operator, which commutes with the symmetry, but what about the perturbation? And so then what we do is we say, okay, we look at the delta function on the lattice, and we could decompose the delta function just basically using the discrete Fourier transform, because you have this cyclic group acting. You can decompose the delta function on the support into the sum of eigenvectors of the rotation. Okay, so this is a discrete Fourier basis, and each element of this discrete Fourier basis has the same support, and and notice that each one lives in the respective eigenspace, which means that I could then write the operator of interest as an explicit rank 1 perturbation of the bulk. So now you could go to town on this by using the Sherman-Morrison-Woodbury formula, because no longer are you looking for, no longer do you have some matrix, determinant of some matrix, it's just a scalar function. but you have to study them in each of these eigenvector sectors. Okay, so what does that look like? Here's the operator. So this is a bulk operator. This has the bands. This is just a translate of the band spectrum plus something, which is finite rank. And let R bulk denote the resolvent of the bulk, the Green's function, or resolvent of the bulk operator, and this one over here be the resolvent of the operator L plus of interest. And here's what the Sherman-Morrison-Woodbury identity looks like. If I take a matrix and add something that's rank 1, then the difference between the inverse of this and the inverse of that has this structure over here. Okay, so you sandwich you sandwich U transpose V in the middle there, like that, and then divide by F. This is a scalar function. So therefore, the poles. So if I apply the formula, then I get this, and so the poles of this the poles of this are just the bulk spectrum. The singularities of this are just on the bulk spectrum. So the poles of this are in the interval of interest are going to be in the poles of this function over here. This function over here corresponds to this F over here. So what I have to study to track the eigenvalues which determine the stability, I have to track the eigenvalues of S scalar functions. S scalar functions, which are analytic away from the bulk spectrum. It's a bit like you're looking for eigenvalues of some operator or matrix which characterizes stability, and what we've done is we've succeeded in factoring the characteristic polynomial somehow into different pieces that can be handled independently. So for each A positive, these are analytic functions, and the eigenvalues are the poles which correspond to the zeros of those. Okay, so the function Fn has only one simple zero, it turns out, in this. One could prove that. I'll show you some pictures in a moment. And so what happens is the discrete spectrum are just, so each of these has one simple zero, and so the spectrum of L plus just consists of these S eigenvalues. That makes sense because we had a bulk operator which just had band spectrum, no eigenstates, and we added something of rank S, and that rank S gives you S eigenvalues. And these might be degeneracies, but they evolve independently with A. Okay, and then so finally, we have to study these functions to determine where the zeros are. We want to know whether the eigenvalues are positive or negative, and so we do some asymptotic analysis of these functions. And what we show is that these functions only have one positive eigenvalue if A is sufficient. There is an A star such that these functions only have there's only one positive zero of any of them if and only if the following criteria is true. And I'll describe the criterion in detail in a moment. So let me just say that here's the structure of the criteria. So this is some quantity which depends only on the band structure. This object here is the spectral projection onto the flat band energy. So there's this infinite dimensional flat band eigenspace, and then we project these eigenvectors En, which that's the discrete Fourier basis, and we want the maximum of these to be smaller than 1 over 2 sigma plus 1. So there's a criteria which, based on asymptotic analysis for A going to infinity and A going to 0, this condition comes out for A going to 0. A going to 0 is a little bit nasty because that's where the that's the limit as you approach as an energy approaches the band spectrum. So the flat band. So evaluating this limit is a little tricky, but one could do it. And so this condition says if some property of the band structure alone is smaller than something about the nonlinearity, then you know that there is such a threshold. Okay, and when this is violated, you have instability. Another consequence is, notice, so this object over here you can expect to be strictly less than 1 because this is a projection, and En is a normalized vector. So since this is strictly less than 1, that means that by taking, if I take sigma sufficiently small, I could always arrange for this condition to be valid. So if I have a nonlinear system where I'm not happy because the flat band states, small amplitude flat band states are not stable, then just by decreasing the nonlinearity, making it smaller, I can stabilize the system. Okay, so this is what, so you have these S functions, analytic functions, and you're looking for zeros of them. And this is how it plays out for the Kagome lattice. At this crossing, when A hits this value, suddenly when you're above, there's a positive 0 and therefore a positive eigenvalue. And this is what you see for different values of A. If A is very small, there's only one positive eigenvalue. One positive eigenvalue turns out not to be a problem because remember there was one orthogonality condition. So that one orthogonality condition was enough to put you into the negative cone of that operator. But as you crank up A, then you get crossings of 0, and each of these is accompanied by another bifurcation, it turns out. Okay. So left plot, right plot. This is what I'll show you just. So we're studying, here is the flat, this is for the diamond lattice, this is the flat band state, and here is that bifurcation that we now understand. And the states, you could see as you, how the symmetry breaking happens. There are a lot of other states, some of which we are able to construct variationally. This is what plotted a bit differently because resolving things is a little tricky. But here again is, this is the case of the Kagome lattice. And it turns out that for the Kagome lattice, I believe here's the, Stephen, this is a value of the critical value. So if you take sigma bigger than this, then you'll always be unstable. But if you're below this threshold, there is below this nonlinearity, you'll always have some range of stable minimal compact solitons. And then for the checkerboard lattice, there's an analogous story where we could compute the sigma as well. So I'll just sum up now. So we have the notion of a minimal compact flat band state. That's just a property of the Laplacian. It's just a minimally supported, highly symmetric, compactly supported state. We have a sharp criteria for stability of these states, and we've applied it to some well-known lattices, diamond lattice, checkerboard lattice, and Kagome lattice. And then by adjusting the nonlinearity, we can always stabilize some range of minimal compact solitons. And we expect that these ideas should play a role in further studies. One example of a further study would be to look at flat bands, systems where the flat band actually is right in the middle of the bulk spectrum. That happens, for example, in the Lieb lattice. And as you vary the vertical coupling in the diamond lattice, those are two examples. So it's natural to expect that there might be some coupling to radiation modes in that case, and so the states would only be metastable. But to my knowledge, there isn't a theory of that yet. And then you could look at other states. So it turns out that there are ways to get there are a lot of flat bands in the physics community are obtained as what are called line graphs of some underlying root lattice. So the checkerboard lattice is the line graph of the square lattice, and the Kagome lattice is the line graph of the honeycomb lattice. And here is the line graph of the triangular lattice. The way you get the line graph is you say that 2 points two points are connected, right? So yeah, let me just say it this way. You look at the midpoints, say, of these edges, and you generate the graph from any two edges which are which share a common vertex will have an edge between them in the line graph. So anyway, these are three examples. We've studied this and this, and I haven't presented anything for this one over here. So, and then also we'd be interested in extensions to 3D. For example, there's the pyroclar, which is turns out to be the line graph of the three-dimensional diamond lattice. And of course, maybe there are experiments that could be done in such systems. And thank you.